So we've had our introduction to the correspondence between a complex number, a plus bi, where a and b are real numbers on the one hand, and a point a comma b in the complex plane, or the Argand plane, in the other side. And so we're really interested in this rich connection between arithmetic and geometry. How are the operations we can do, addition, subtraction, multiplication, division, and so forth, we'll talk about a few more, that we can do arithmetically on complex numbers? How are those operations manifest in the complex plane? What do they look like if we visualize them inside that two-dimensional diagram? And vice versa, how can our diagrammatic, geometric thinking, our intuitions over on the geometric side, help us to better understand what's going on with the arithmetic operations on complex numbers on the other side? We want to build that two-way dictionary so we can translate in both directions between arithmetic computation and geometric visualization. So what does that look like? So we saw in our last video and talked about how a complex number and a vector in the xy plane have an awful lot in common. They can both be seen as vectors, because after all, what it means to be a vector space is that we can add and we can multiply by scalars. Well, we can do that with complex numbers also. We can add two complex numbers by adding their real parts, adding their imaginary parts. We can multiply a complex number by a real scalar, just by multiplying each of the real and imaginary parts by that scalar. And so the complex numbers can form a vector space over the real numbers. But, as I mentioned in our last video, we get with complex numbers a lot richer arithmetic than we would have gotten just by treating them as vectors in the xy plane. And so our big goal this week is going to be to explore that additional bounty that the complex numbers give us, both arithmetically and geometrically. So here are a couple examples of operations we can do with complex numbers that we wouldn't have thought about doing with real numbers. Well, maybe, but not quite in the same way. So one operation is called the complex conjugate of a complex number. So the complex conjugate of a complex number is just another complex number where we've taken the imaginary part and we've just flipped the sign, either negative to positive or positive to negative, right? So we've just opposited the sign of the imaginary part. We've left the real part alone. We denote the complex conjugate of a complex number z just by putting a over bar on top of it. So z bar is what we would call the complex conjugate of the number z. So that's kind of a new operation for complex numbers. If we try to take the complex conjugate of a real number, we end up getting the same real number back. So we can't tell that we've done that, right? Because the imaginary part of a real number would just be 0. And the opposite of 0 is 0. So real numbers have the unique property that they are equal to their own complex conjugate. So that's why that's an operation that we might not have done before with real numbers, because it doesn't actually do anything to a real number. Similarly, we have an operation on complex numbers that's called modulus. The modulus of a complex number, if it has real part a, imaginary part b, is the square root of the sum of the squares of a and b. So square root of a squared plus b squared. And you'll notice that for modulus, we use the notation of vertical bars to represent the modulus of a complex number z. That's not an accident, because if we are starting with a real number, let's say b is equal to 0 here, so this has a 0 imaginary part, then what would happen if I took the square root of a squared? Well, what I would end up getting, as our calculus students are so apt to forget, is not a. The square root of a squared is not a, but it's in fact the absolute value of a, because the square root here is always going to give us a positive, or at least a non-negative, answer. And so we use the vertical bars for the modulus of a complex number because it's a generalization of taking the absolute value of a real number, in that the result is always a non-negative answer. And it also satisfies all the other properties that we would expect an absolute value-like thing to satisfy. Now, we should be very careful whenever we talk about square roots. It should give us some pause and maybe a little bit of heartburn. But in this case, because a and b are real numbers, they're the real and imaginary parts of z, and therefore they are themselves real. If I square a and I square b, I'm guaranteed to get something non-negative, because a and b are real numbers. Again, being very careful to bracket that, both for our own understanding and maybe more importantly for our students' understanding. And so our intuition that a squared and b squared are going to be non-negative, and therefore a squared plus b squared is non-negative, that still holds here because a and b are real. That way, we don't have to be worried about taking the square root of a squared plus b squared, because it's the square root of a non-negative real number, and therefore this square root is going to give us a non-negative real number. And so in particular, this also means that when I take the modulus of a complex number, the result always comes back real. So that's one way of taking a complex number and giving us a real thing that helps us to measure that complex number. Now, one of the things about the modulus that also makes it similar to the absolute value of a real number is that it measures the distance of that number from the origin. In the case of the real number line, the absolute value of a real number tells us how far on the real number line that number is from the origin, which is the real number 0. Well, what about in the complex plane? In the complex plane, the modulus of a complex number measures for us how far away from the origin of the complex plane is that complex number. So the complex number 1 plus 1i, for example, if I take the modulus of that number, it's the square root of 1 squared plus 1 squared, the square root of 2. That also happens to be the Euclidean distance from that complex number in the complex plane to the origin, 0, 0, which is also the real number 0 in the complex plane. So this also gives us a really nice geometrical intuition for why it is that we use vertical bars to represent the modulus of a complex number. We're measuring the distance, except now it's a Euclidean two-dimensional distance from that complex number in the complex plane to the origin in the complex plane. So the modulus can be thought of as that distance to the origin in the complex plane, which also means that anytime we're playing around with the modulus of a complex number, if we're looking at it in the complex plane, it might be helpful if we, instead of used rectangular coordinates, we could use polar coordinates to get a better sense for how we're locating these points. So if we just toggle, instead of using a rectangular grid, we toggle to a polar grid. Now we get a little bit better sense of how this is working, right? So if I have a complex number, let's say it's right here or so, it looks like this complex number lies on the circle that has a radius of 2 centered at the origin, and sure enough, its modulus is, well, approximately, couldn't get quite there, equal to 2. So remember, in polar coordinates, all of our grid lines are showing us how far away from the origin we are, 1 unit here, 2 units there, 3 units to the origin here, and so forth. And it's also showing us the angles. The angle measured from the positive real axis to the segment from the origin to my number. Right? So that angle can also be used to help us to characterize a complex number. We just give it a slightly different name when we're talking about it in the complex plane. Instead of calling it the angle as we would in polar coordinates, we call it the argument. It's another A word. So we call the principal argument of a complex number that angle between negative pi and pi, for which the real part of my number is equal to the modulus of z times the cosine of that angle, and the imaginary part is equal to the modulus times the sine of that angle. So that's kind of a fancy algebraic way to say what it is that we're doing when we compute the principal argument, and we use capital A arg to talk about the principal argument of a complex number. But really, it is nothing more than the polar coordinate angle measured from the positive real axis to the segment from the origin out to that complex number. So for example, if I'm on the imaginary axis, let's say I have a number like 2i here. On the imaginary axis, the modulus of this number is just going to be equal to 2. The square root of 0 squared plus 2 squared, the square root of 4, going to give me 2. And the argument is going to be the angle from the positive real axis to that line segment. And that angle, measured in radians, we're always going to measure angles in radians as far as our coordinate systems are concerned, that angle is going to be pi over 2. So there are kind of two ways to express this complex number 2i. We can represent it with its real and imaginary parts, 0 and 2, respectively. That's rectangular coordinates viewpoint. Or in the polar coordinates viewpoint, we can represent it by its distance to the origin, which is 2, that's its modulus, and its principal argument, the angle to the positive x-axis, which is pi over 2. So those two different coordinate systems that we can use in rectangular coordinates give us two different ways of expressing a complex number, by either its real and its imaginary part, or by its modulus and its argument. So both of these viewpoints are going to be helpful for you this week as you explore the question of how does complex number arithmetic manifest as complex plane geometry. So in our final video, we're going to talk about what is the task for this week. What do I want you to explore? What do I want you to write up? And what are the connections ultimately that we're hoping to forge this week?